things that occur in that worksheet, or that in the textbook questions there. First is this. There's actually three major things. If you have two charges, one is a positive and one is a negative, they obviously attract to each other. Now yesterday when I used the pith ball, you saw that when the rubber rod touched the pith ball, they became the same charge. So what happens here is when these two guys touch, they end up separating after they touch and sharing the same charge. So if you have 20 and minus 5, that means you have a net of 15 microcoulombs. So when they split apart, they each take the same amount of charge from it. So now they both have a plus 7.5 microcoulombs of charge. So when you readjust the question after they have touched, you now find the force between them with their new charge using the law of electrostatics, Coulomb's law of electrostatics. Okay? So the biggest thing is when they touch, they share the charge and split and have the same amount of charge when they have come apart. Okay, so there was the first thing that you saw yesterday that some of you should have had a question about if you got to those problems. And that was in question 2. Question 3. I didn't do this yesterday, but I sometimes do. If I have two pith balls with the same charge and they're both hanging, they're going to be separated. Now this question you'll see over and over again. The only information that will be given to you is the mass of the actual pith ball and the angle between them as well. So we got to find out the amount of force. Morgan, go stand at the back and lean against the shelf. Okay. So the first thing I do, I find out what the force of gravity is on this guy. Okay? So force of gravity is the mass of the pith ball, which is
0.05 grams.
0.05
That's grams though.
grams, right? So then divide that by 1,000 to get it into kilograms, and times it by 9.8. Now once I have that mass, once I have that force, it gave you the angle of separation of the two ropes, correct? The angle of separation was what? 10 degrees total? Okay, so that means that this is 5 degrees. So what you're able to calculate then is the force of repulsion between them. Once you have the force of repulsion between them, there's two things that they could ask for you. They could just ask you what the force of repulsion is between them, or they could ask you what the magnitude of the charge is on them if they have an equal charge. So you'll see this a number of times as well. Now, because they have equal charges, I'm going to make each charge x here, divided by d squared. Now they must give you, no, in this first question they don't give you the distance, so we don't need any of this, we just need to find this here. Alright? In the second question they're going to give you either the length of the string, meaning you'll have this distance, or they might give you the distance of separation between them. If you've given this distance, and you find the distance here, you have to multiply it by 2, because that's only half the distance. Alright? So then what I do is I have x is equal to the square root of fd squared over k. Now I'm leaving this fairly vague to you, because I want you actually to do this on your own on the sheet. But for right now, I'm just kind of showing you how you go about it. So they may give you the length of the string. They may give you the length of the entire string, in which it pinches in the middle. They'll sometimes do that. So then your distance here is half of the actual length of the whole string. And then you have to find the distance here and times it by 2 to get the distance of separation between them. Okay, so there's a number of ways that this question will expand on you. All right, the first way in number 3 is just find this force here, using force of gravity, that angle, to get that force. Okay, in number 4, they give you a distance, so you need to find out what the charge is on it, and you find it by taking the square root of F times B squared divided by K. All right? So that's the second thing. Again, most of you should have, I would suspect not many of you got past the first question in this, on the first problem, because you should have run into these issues already. All right? And the third and final thing that happens is this, is if I have three electric charges, I need to find, they're going to ask you for the net force on one of the 3 these charges. So what happens here is this. The first thing I do, let's say I'm trying to find the net charge on A. So how does B and C affect A? So I do this a little bit different than the book. The first thing I want to do is find out what the force is between A and B, and the direction in which it's going to move. Which way is A going to move because of B? Towards it. So it's going to move to the right. Then I got to find out the force between AC. So as if this guy doesn't exist. Which way is A going to move because of C?
Right.
It's also going to move to the right. So then when I calculate this and add them up, I'm going to get a net force on A moving to the right. Okay? So both of those charges are going to pull the A to the right. Let's look at the net force on B now. So, which way is B going to move because of A? To the left. Which way is B going to move because of C?
To the left. To the left. Oh, left, sorry.
To the left as well. So its net force, of course, is going to be in the direction of left. Okay, now I'm not calculating any of this, I'm just showing you how this works. And then finally, let's look at the net force on C. So force AC, which way is it going to move because of A?
Left.
To the left. Which way is it going to move because of B?
Right.
To the right. And then when you subtract them, whichever one is greater, that's the direction in which it's going to move. Okay, so I can't tell that unless I know the actual magnitudes. And again, for all of this, you're using KQ1 Q2 over D squared. Okay? All right? Any questions so far about that? So that basically takes you through all 7 of those questions. Number 5 uses electric field intensity, and that's about it. Any questions about that so far? Okay, so I'll give you some time a little bit later this morning to do that. All right, take a look at the next thing on page 394. Potential difference. So let us consider the work done by gravity on a wagon coasting down a hill. The wagon is within gravitational field of the earth and experiences gravitational force causing it to travel downhill. Work is done by the gravitational field, so the energy expended comes within the gravitational system. The wagon has less potential energy at the bottom of the hill than it had at the top. In order to return to the wagon to the top, the work must be done on it. However, in this instance, the energy must be supplied from an outside source to pull against gravitational force. The energy expended is stored in the system, imparting to the wagon more potential energy at the top of the hill than it had at the bottom. Okay, so basically what it says is this. If I have a roller coaster, and you go down, you start at the top of the roller coaster up here. You have a certain amount of potential energy that's being done. As that roller coaster comes down here, your potential energy at the top starts to get lower, but the kinetic energy, the energy in motion of the roller coaster, starts to speed up. But what you're going to find out is this, is that this roller coaster will not go back to the same height as it's been released. Okay? Now why is that? Because in theory, if it should go right back to the top, to the same height. But what affects it so that it can't happen? Mostly friction in this case. Because gravity doesn't change. It pulls it down the same direction, the same amount as it does pulling it up. Right? So it's basically friction that says that if this roller coaster comes down, it's not going to make it quite back up to the height that it started at. Okay? In order for it to get back to that height, you'll notice, some of you have been on a roller coaster before, some of them will have a chain right here. And it'll pull the roller coaster back up. So there has to be work done on that car itself to get it back to the same height up there. Okay? So the potential energy that we have here is not the same as it is here because the height is different. Therefore, the work has to be done, and there's a change in potential. Okay? The same thing happens when an electric charge moves from one spot over to another. There's work being done on it. Okay? And it has a different potential here than it does there. So, I should put this actually as negative charges, because those are the ones that move. So negative charges, okay? So, if work is done, so similarly, a charge in an electric field experiences an electric force according to Coulomb's law. If the charge moves in responsive to the force, work is done by the electric field. Energy is removed from the system. If the charge is moved against the Coulomb force of the electric field, work is done on it using energy from some outside source, this energy being stored in the system. If work is done as a charge moves from one point to another in an electric field, or if work is required to move a charge from one point to another, these 2 points are said to differ in electric potential. The magnitude of work is a measure of this difference in potential. The concept of potential difference is very important in the understanding of electric phenomena. The potential difference between 2 points in an electric field is the work done per unit charge as a charge is moved between these 2 points. Okay, potential difference. How many of you have seen 9-volt battery before? That 9 volts, some of you haven't seen a 9-volt battery before? Seriously?
No.
You have?
I have.
Okay, good. Alright, so the 9-volt battery, alright? We mentioned that it's 9 volts. This is where we learn about potential difference. It has a potential difference of 9 volts, meaning that the ratio of the work being done to move that charge is a ratio of 9 to 1. V represents potential difference. W, of course, is work. And Q is the quantity of charge. So 1 volt of potential difference is equivalent to 1 joule of work per 1 coulomb of charge. Okay? Now, we in the past have talked about work being force times distance as well. So we're gonna look at that a little bit more. You need-
She had it incomplete on her, she needs a picture of her head,
Okay,
so we gotta get that done, because
yeah,
she's lucky she phoned me back.
alright, okay. Alright, the unit of potential, so we've done that. They do use microvolts a little bit, megavolts, but for you in all your work, you just need to make sure that it's in voltage. Alright, now yesterday I told you about electric field intensity. Electric field intensity, E equals F over Q, in which that's newtons per coulombs. So this is electric field intensity. You need to make a note of this because I'm about to talk to you about potential gradient, which measures the same amount of quantity but has different units. Potential gradient is the potential difference, the ratio of the potential difference over the distance. So it's volt per meter. We call this potential gradient. The only difference between these two, when written out, is this one has units of newtons per coulomb, and this one's volt per meter. But they're the exact same amount. So if you find one, you find the electric field intensity, to change it to potential gradient, you just change the units on it. And that's it. The electric field intensity is commonly expressed in terms of volts per meter and can be referred to as potential gradient. The potential gradient of an electric field is the change in potential per unit distance. Okay? So that's the first part of the new stuff for you today. How many of you got started on those 7 problems yesterday? How far did you get?
3.
You're in question 3? Pardon me? 3? Anybody past that point? You guys?
I think we're on 5.
25? Okay. Alright, I'm going to actually give you time today to work on those questions right now before I go into capacitors. Grade 12, you guys did capacitors last year, so you can probably look at it. So, for right now, I just want you to make sure that you're done all of the Group A questions. Go through them. The textbook beside the pencil sharpener has the solutions to all of this. So, you got time right now to go through all those 7 problems. And, okay?
What'd you get? I got, what, 2, 4.
James, can I see it?
Wow.
You got it?
Nice.